All right, so to end up this section, we're actually going to double back on kind of where we started, which is going to be this big quest of trying to identify a whole bunch of inverses. Because that's really the big thing that we're going to need out of all of this, is we're going to have to begin thinking about how we're going to encrypt things and move things around. So we needed this star operation to kind of do some proper scrambling. But we also need to know how to undo the scrambling, which is going to be about finding inverses. So that's where we're going to double back to. So the kind of big goal in all of this is that you're going to give me some polynomial A, and my goal is to identify what its inverse is going to be. The first thing we need to know is we need to know what things are actually going to have an inverse. So inverses are going to exist provided we have some type of GCD, which is going to be a 1. So here the GCD is then going to be computed with the polynomial A, and we're going to begin comparing it with this polynomial x to the n minus 1. So ultimately, that's going to be the thing that we are going to reduce away. So we're going to work in these little quotient rings. So we're going to reduce all of those exponents modulo A. We're not going to do it yet. And that's where there's going to be a little bit of kind of delicate ordering that has to occur. So we're going to compute the GCD of your input polynomial A against the x to the n minus 1. But you're going to be doing this at the level where you're only reducing the coefficients modulo P. No reduction of exponents. If you did the reduction of exponents already, you would see that that x to the n would kick out a 1. So x to the n minus 1 would be a 0. And then you're computing GCDs against 0, and it's just all around bad news. So there's going to be kind of a layering process in that you're going to be doing work up here initially. That's then going to tell you that if it kicks out a 1, we know that this A is actually going to be invertible. The actual inverse that we're finding is actually going to live down in the z mod pz modulo x to the n minus 1 world. So that's ultimately where we want to live, but we have to live a little bit higher and then push it down from there. So just kind of realize the steps that are going to occur there. So if we have a GCD of 1, we know that this extended Euclidean algorithm is going to find these special little functions, which we can call u and v, that are going to give you this equation is true. And again, this equation is true in the z mod pz bracket x world. So it's just where we're reducing the exponents modulo p. So then the last part about it is then going to be to turn this page into reduction of exponents modulo n, which is going to say bring about this reduction modulo x to the n minus 1. Well, that turns x to the n minus 1 into a 0. So that whole expression right there disappears. So now you can see that you have a times u equals a 1 in this crazy little realm, which tells you that u is the inverse of a because they multiply to make a 1. And that's our goal for inverses, is that I always want things that when I multiply them together, they're going to give me a 1, and it has to occur in the correct space. So it's going to give me a 1 provided that I have my reduction of coefficients modulo p and my reduction of exponents done modulo n. So in our first example, we can actually run this little game. So I'm going to have my n, which is a 7, and my p, which is a 3. And my goal is to identify what the inverse of x to the 4th plus 2x squared plus 1 is going to be. And here I'm going to kind of just showcase that I've done all of the written steps, but I don't want to kind of go through that whole long process of back substitution and all of that. But realize that you can find those very quickly. Well, not very quickly, but doing a little bit of work, you can actually run that. So our goal, again, is going to be to find these u's and v's that'll actually showcase what the inverse will be. So to do that, you need to do this division of take x to the 7th, because we're working with n being 7, divide that by x to the 4th plus 2x squared plus 1. You're going to keep doing that until you can see that remainder of a 0. Again, the last non-zero remainder is then going to be your GCD, and we really hope that it's going to be a 1. So you can do your first little bit of division, which happens pretty quickly. So hooray, we end up seeing a quotient of x cubed plus x, and we're going to have a remainder of 2x plus 2. So again, if you want to go through that arithmetic, you can, or just pause it to run that. So then you have to do that a second time. So now you're going to take that previous quotient, or you're going to take that previous b value and now divide it by the newly found remainder. So you're going to take the x to the 4th plus 2x squared plus a 1 and now divide it by 2x plus 2. I specifically constructed these ones to be really nice because I wanted this thing to terminate relatively quickly. which we can see, in fact, does work. There is a little bit of comment to be made actually in the very first step of this one, because you have this x to the fourth, and you want to know what can you do to get that 2x into it. So it's kind of awkward because there's not a coefficient in front of the x to the fourth. So here's where you're going to have to remember that 2 times 2 kicks out a 1 modulo 3, because my p is a 3. So when you have this 2x and you're going to multiply it by something to get you x to the fourth, you're going to actually add in another 2, and then you're going to add in the x cubed. So realize that sometimes there'll be that kind of weird process, is that you actually have to have the inverse of 2 modulo 3, which happens to be a 2 in this scenario, to then get you that little 1. So the ones I'll make you do by hand only usually you have this reduction modulo 3. So if there's a 2, you just got to bring about another 2. But realize that if there's more complicated p's, there'd be a little bit of additional trickery happening there as well. So you run that little process. Again, you're going to see that remainder of a 1, which technically tells me that my next step is going to 0 out. So I didn't actually go ahead and write that one, just because you have the 1, you know the next step is going to 0 out. So that immediately tells you that the GCD between the x to the n minus 1 and a is a 1. So I know that I'm going to be invertible. What I need to do then is I need to do this back substitution. So you take that green equation, you substitute in that blue equation, do a tiny little bit of distribution, and you end up with this big ol' expression, which again is still equal to a 1. So I'll let you kind of explore that on your own. And you get that type of statement that's going to have some giant chunk multiplied by an a. So it's a u times an a. And then we're going to have this v times the x to the n minus 1. When we reduce those exponents modulo 7, that whole part disappears. So this u thing comes down, the a thing comes down, and voila, whatever that u expression happened to be is then going to be my inverse. So it's not a terrible process. It's kind of terrible to do by hand, but it's not a super duper awful process in that it does get sped up pretty quickly. And if I jump back to some Sage code, I can kind of show you what's happening there. So let's run down to this little example. Cool. All right. So here's my example where I was just playing with. So I have a p, which is a 3. I have an n, which is a 7. I'm then going to have my a value, which is then going to be fed in as my x to the fourth plus 2x squared plus a 1. So what I've built actually is then going to be an inverse mod function. And the way that this thing actually functions is that it's going to eat in whatever a, it's going to eat your prime, and it's going to eat whatever your exponent reduction n happens to be. If the GCD is not a 1, it's going to return false. Otherwise, it's going to do this extended Euclidean algorithm, and it's going to find that little function that multiplies with the function f or a or whatever you're playing with, paired with the other x to the n minus 1, which would then have the v function. So we're going to grab that one and return that back to the user. So if you want to kind of see the steps of what's happening there, you're going to have my function a. If you run this xGCD, it's going to return the GCD, which is a 1. So that's what's happening in my if statement. I'm making sure that it's a 1. Then it's going to create a u value, and it's going to create the v value. And we're going to return this u value because that's the one that's paired with the a. So that's what this step is then doing, is that it's grabbing the index 1 entry of that. And that just depends on the order that you feed those into. The very last step is I actually ran that expression through a reduction just to make sure that it does in fact have the correct coefficients and everything is reduced so nothing funky actually happened. So that is my last little bit, is just to make sure it's reduced and then print that thing back to the user, which in that example, nothing actually happened in the reduction, but just to be safe, I just pushed it through that so that we have this really nice little inverse. So it's a cute little game in that it's not really cute when you have to do it by hand, but realize that later on we're going to have this inverse mod poly. So in the actual Sage, they have this like inverse mod command, and now I made it with polynomials. So I have to eat in a function, eat in the prime that my coefficients are being reduced modulo, and then the n, which is what my exponents are being reduced modulo. So once we have that, we actually have most of the tools that we need in order to begin attacking some of these actual crypto systems. And then we begin kind of exploring some of the nuances and how to actually view this as a lattice problem and all of the fun that emerges from that as well. So enjoy.